that really put a lot of effort in our project in this medical analysis, where they do a lot of labeling and a lot of data collections, and was really and make also the software that we developed into free access to many of the poor people. So this was a tremendous effort from the medical side. So I owe a great deal to all these people's collaboration, and so that's the background. So today what I'm going to talk about was really the medical analysis that we were involved in for many years, and then eventually led us to thinking about some of the mathematical foundations of transfer learning. So what is transfer learning? Transfer learning is a paradigm that is known and very well adapted and exploited in computer science domain, which is a very simple principle that you have a lot of effort of doing some learned task. You already have optimization problem, for example, you have solved, and now you wanted to leverage this knowledge. Okay, so in comparison to the traditional machine learning, where you have isolated single task, then you just try to come up with a criteria by which you are going to learn the system. And then you have the database, then you run the system, you use neural network, or you do whatever your tools at hand, and you get to the solution. And then so the tasks are isolated. Where transfer learning is, you have a task now you need to leverage, you need to finish. Then you look around to see what other related tasks you have that you have accomplished. And then you try to learn from the previous task and try to leverage the knowledge. So the isolated tasks are connected in this very, very interesting way. And when do you do this? Transfer learning usually is when you have a new task, and in the terminology, is called target task. So that's your target. That's very easy to remember. But this new target task has very limited data, or have very limited and relevant data. You may have a lot of data, but many of the data is useless. And so you're going to look for some other previous knowledge. So some early tasks that are called source tasks. That's your source of inspiration. And the criteria are that if there's a similarity between the target task and the source task, then you try to draw the comparison and try to leverage the knowledge, okay? So one of the most well-known transfer learning is probably now, because of ChatGPT, the large language model. So large language model are really models where you use a huge number of data and a large network where you train a lot of things. So you say that this is a language, I try to say a question and answers. And then you try to collect as many as possible, all these relevant data, and then you train on the data. And then when you do get so this is called pre-training. And when you do get a specific question come in, then you started narrowing down all the previous tasks and look for specific domains that are relevant to it. And then, of course, still those knowledge you have trained may not be exactly what you're looking for. Then you have to, in the neural network, you have to do some fine tuning to try to narrow down and supplement and try to find the most relevant knowledge for which you can try to give the answer. Okay, so this is the very high level conceptual understanding of what transfer learning. But transfer learning, unlike many of the CS specific technologies, is a very generic philosophy. So whatever the new CS tools you have or machine learning tools you have developed, you can always apply this methodology, right? So it has been very popular in all sorts of areas, which is from computer vision or natural language processing or medical data, and recently some other works along with our collaborators to the financial data. So I'm going to come back to it, some of this, okay? So for us, where do we start this transfer learning? it really started by the group of doctors presenting this data to us and asked us about this early diagnosis of retinopathy of prematurity. I'm going to call it ROP. Okay, this is a very less known eye diseases, but very important diseases that has a significant impact on us. It specifically happened to infants that are premature and are born prematurely, usually before the weeks of 31 weeks, and also their weight is underweight. Okay, this kind of there are various conjectures of why this group of infants are more vulnerable to this particular eye diseases. One of the conjecture is probably because they were put in this ICU and warmer, and certain stimulus and light and certain things could have affected their blood vessel growth. And as a result, so the eye in the retina, so the eye, there's a abnormal blood vessel growth in this very sensitive part. In this very sensitive part of this eye is called the retina. Okay, and if you look at the picture here, well, the healthy one, you can see the vessel, the blood vessels are very thin and very evenly distributed. But then if you see the one with the disease, you can see some overgrowth of the blood vessel. Okay, so this kind of overgrowth blood vessel is very dangerous, and it really could cause blindness if it is untreated. The only good news about it is this type of eye diseases for infants is, if it is diagnosed earlier, is reversible. But if it is left undiagnosed, and then when it grows, then it could really cause the detachment of retina, and that's really very dangerous, and it leads to the blindness. Okay, so what is difficult? The main difficulty of having this early diagnosis of this ROP, well, first of all, I'm a parent. I was not aware of this kind of disease for the kids. And usually for many of the infants or young adults, they don't have the eye checks until the age of 3 or 4 or even later. Okay, and when the infants have any eye problem, they couldn't talk. I mean, it's very hard for them to express. So the awareness of this ROP among parents and even doctors is very limited. And the result, the data are very limited. And also because infant has limited communication capacities, you really have to give higher degree of requirement for this diagnosis specificity. So which is oral sensitivity, meaning if you do see why, you want to catch up with the diagnosis as early as possible. So for medical data imaging analysis, usually this kind of problems, it requires tens of thousands of data to get to a desirable accuracy level. Whereas for this ROP, it's very difficult to get them. Most of the data available is in terms of a couple of $1,000, a couple of thousand data, what I'm doing here. And then there's a balance between the positive and negative. Positive meaning you have the ROP, and negative image is very unbalanced, just because that you don't have many. The labeling of this particular data is very costly and label intensive. That's why we have this doctor who are really helping us. And each night, they can spend the whole night only producing a label of 10 to 20. So if you want to get thousands of data, it really takes a long time to get to the desirable set of data. So when we got these questions from the doctors, then the question for us is, well, there are two ways we could do. We could start with the direct analysis of the ROP, or we can actually leverage some of the other eye diseases that are much well known because eye structures are very similar. So we started thinking about this transfer learning. And of course, as I said, the ROP data set we have was about 2,000. And then the negative samples and 800 positive samples. So the ratio is very unbalanced. Then we were thinking about maybe there's another much well-known diseases, which is called DR. what is DR? DR is much well known because of the huge populations of people that have diabetes. Okay, diabetes is in terms of the hundreds of millions of patients globally, and for all those people that have diabetes, about 10 to 15% of them would also have associated eye diseases called diabetic retinopathy. Okay, and it's a very similar phenomenon, which is the retina got this high blood sugar level causes this blood vessel to swell or leak. So there's also some abnormality of this blood vessel near the retina. Okay, so that's a similarity between this ROP for the infants and this DR for the diabetic patients. Okay, and the good news about the diabetes is because of the huge populations of hundreds of millions of patients, and then also people are adults, they are more aware of this. So they are the available data for DR is in terms of millions of data points. Okay, so this is, and also the significant improvement in diagnosis of DR has really reported in the last decades, starting from 2015 and 16, including this very well-known work in JAMA, and also some of our own efforts that have been now used in many of the free access for peoples. That, for example, if you take the retina image of the patient with DR, and if you take about 10,000 of them, that's enough for to get the desirable accuracy or the sensitivity analysis. Then you build a convolutional neural network. This is basically a classification problem, which the neural network has two different part of layers. One is about feature extraction, trying to find the features that are related to the disease, and then you create a distribution of this diseases, and then you can have the classification, and that's you have another layer of what they call classifiers that give you the output of depends on your the desired results. Either you say no DR, or severe one, or the one that is really at the final stage, or you just look at 0, 1. So it can depend on your classes that you're looking for. Okay, so this is the existing knowledge about the diseases for eye diseases related to DR. And now you can look at, so this is just one of the pictures I'm showing you that we run on our computer to show that in general, if you have about 10 to 15,000 patients, and then has about 30,000 of the resized and images, then you can get very nice results about the accuracy and the sensitivity up here. And I want to say, just for those who are not familiar with certain criteria of sensitivity and all the things, is basically sensitivity, meaning if you have the disease, I will be 100% catch it. And the specificity is if you're healthy, then I should be able to catch up with the healthy one. And the accuracy is the basically the total number of correct diagnosis over the total population. Okay, so these are the different criteria, and the scores here basically just show you how progressed and how advanced now using machine learning to diagnose this DR has been really satisfying. It's over the 95% of the desirable level. Okay, and for us, the practice for us to start from using the DR to this to ROP is, of course, similar things. Is we have this retina image, which is CFP. We call it CFP. Is basically you go to see a doctor, you put your head in front of that machines, then they take this color fundus photographs, okay, and then see your image of the eyes. And then you can actually create a feature space, cut and paste, and then look at the feature space, and then look at the distributions of this different images. And then you try to do this feature extraction and the classification. So what is a false positive risk? So the false positive risk is very low. So in that sense, we are trying to be as much aggressive as possible, because even if you have, usually doctor will not immediately give you an operation. Instead, they will do a second test or doing more in-depth analysis, taking more photos, and then, for example, for glaucoma, that's one of the diseases. Doctors will observe you over a period of two years, in fact, and then every 2 months or every few weeks ask you to come. And then many of the diseases progresses slowly. So they wanted to be sure to take enough photos, and then over a period of time to see the progression, and then make sure they get the right diagnosis. Then they started doing this operation. So false positive is not a high risk, okay? Yeah, so this is the DR, and then of course this is the DR images that you can see. So now you look at this, and then we started looking at when we started having these ideas of doing transfer learning from the DR diagnosis to ROP diagnosis, we start looking around to see this existing literature, to see who has done what. And then to our surprise, that in this medical image analysis, transfer learning was already exercised for over 20 years. However, the interesting thing is, in the transfer learning practice, at least in the medical field, what they did was not looking at the similar diseases such as this DR for the ROP. What they did was to look at millions of generic and very generic pictures of landscaping or animals and everything. And then they try to study the feature space and then create the distributions, and then try to label them into thousands of data classes, and then use that as a basis, or what we call source task, to learn. So for us, this is quite surprising that you have a particular eye diseases, and then you go to the general landscape and try to do a transfer learning. So what we did was, immediately we try to compare these two different source tasks. Okay, one is using these generic images to learn the features and do the classification, basically redesign the neural network structures and then add a few layers and then try to do it. And similarly, we do this with the DR, which is more relevant images, and then trying to transfer the knowledge. Okay, and then we want to see, and of course, intuitively, you would expect much better results for the second one. And I see a question.
She knows a question in chat. Ask for more clarification about the false positive rate and whether the false positive rate, what is the false positive rate for the initial test?
At DR, I don't know the at DR initial test. For us, when we did this, we used this DR analysis, and we have this tables, and then train this over, we eventually trained over 150,000 data points really to get to the last one. And then what we did was we give it to the doctors, and doctor use it not as a diagnosis tools, but as a diagnosis assistant tools, because these days for any of the AI assisted techniques, it's a lot of gray area, and who is going to be responsible for what. So in fact, we are just providing this to this doctors to help the analysis. What is the prevalence of PR in the population? Oh, DR. So it's for ROP. That's a good question. So the ROP, they're estimated about globally about 19 million cases that are related to this eye retinal diseases that people, infants have this eye problems. And about ROP contributes anywhere from 6 to 15 or 18% of these diseases leading to the blindness. And for this DR, the prevalence, as I said, we have about, in China, for example, there is about estimation of 20% of the population that are having either explicit or implicit of diabetic. And then among them, about 20% of them also get affected by the DR. Okay, so yeah, let me come back to this this analysis, which is, you see this comparison, which is quite compelling, that shows that the noun means that this is a direct learning. You just directly build a neural network and trying to detect the ROP. And these are the numbers that are not as desirable as you see, even in terms of especially sensitivities that are pretty low. And then if you use the generic first transfer learning techniques, then what you see immediately, the main sensitivity analysis are also DR that jump into 92. Whereas the DR, which is really found from the retina images, then the performance here really still dominates the one from this generic image. Okay, so these are the numbers here. And also in terms of this robustness of this DR, is really the robustness of DR really is much more significant when you have a limited training set. Let's take 10% of the training set. Then the improvements and especially I didn't show the picture, the number here, the stochasticity is much lower. The variance is much lower, and the improvement of the accuracy is also much more significant than ImageNet. Okay, so that's the motivating example when we were doing this practical analysis for doctors and trying to help to do this analysis. Then it's really the beginning of our research. Okay, so we learned this transfer learning, and from the way I described to you, at least for many of people like me coming from more of a technical background, still this transfer learning is not understood mathematically. Exactly what are you doing here? You say that I have the data, I transfer, and then I do a neural network, I did something. So how do you really describe the transfer learning? And the other question for us is really relevant is, do I start, if I have a transfer learning approach, can it be always guaranteed that it is feasible? Meaning there's always a solution of some sort. And also in this particular examples, when we actually start with the eye disease diagnosis, the question is obvious. Do I start with other eye diseases and transfer, or do I start with generic classification images and transfer? How do we differentiate, or among choices of candidates, how do I find the most suitable one? Is there any criteria for us to measure this transferability? So that's the question that we abstract from this very practical analysis. Okay? So to understand this, we look at the existing literature and found out most of these transfer learning are very task specific, and then it's really focused on the one particular aspect of it. Either you look at the transferability saying, well, the target goal is the same and the final classification classes are similar. I just adapt the data from one data set to the existing data set, and that's called domain adaptation. And then because you're transferring one data set to another, you can immediately see there's a connection of this optimal transport. And then you can also use various divergence functions to compare the distributions of data. So that's one of the main ideas in terms of domain adaptation or optimal transport that are looking at the one particular aspect of transfer learning and then trying to measure the error using various divergence functions. And then the other one is classification. So instead of the initial data, you look at the end data and look at the output of this and trying to measure the relevance of the transfer learning. Okay, so for us to actually try to to answer the question we proposed here, we have to come back to the drawing board and say, what is this transfer learning? Transfer learning starts with a source task. And the source tasks really start from, I use S, okay, to refer to anything related to the source task. So access is your initial image. So if you think about the classification problem of this retina image, so access is the retina image, okay? And then what you want to do is to say, given the image, whether it's 0 and 1, 0 meaning is negative, 1 is positive. So this is why S is the label. So you have this label space, okay? So this is called input, image, output is your classification, okay? And then of course you started doing various controls or models, and then or you try to apply different neural networks to approximate it. So what you end up seeing is, I give you an image, you have a model, and then the model give me a predicted label, say 0 and 1. Okay, so this is the model label, this is a 1. And then you have usually in this particular classification problem, you take a loss function, which say, for example, you take cross entropy functions, okay? And then you compare the loss function between the true label, this is a bad or good, versus your prediction, okay? So the loss function with respect to this difference of this labeled data and the predicted label. So this is what you're trying to do, is basically an optimization problem on this side in the source task. That's what we do. That trying to find the appropriate models among all the choices of models that, so this is the FS, is all the possible models you're going to do. And then you try to solve an optimization problem. Very easy, okay? And then on these target task, is almost analogous, except I change all the S into T to view it as a target task. Again, you have the loss functions, you have the models here, and you have the comparison of your model versus the reality, and you measure the loss. And everything is, your input is XT and the output is YT. Okay, and then you think about this, and I'm not going to bore you with all the details of Banach space or with the proper measures or and the metrics and so on and so forth. But this is, you can imagine, this is just the data and the model and try to find the best fit with the proper choices of error functions. So what exactly is transfer learning? This is a graph that it took us a while to really come up to try to understand, summarize all this practice of transfer learning. This is really, transfer learning is in fact a 3-step procedures. Instead of going from the target task with the data, goes all the way with the direct learning to find the best model that give you the right label and so on and so forth. What you did was, you have a source task, okay, and you have the source input in the image here, and then you have already a model that you know, that's a F star S. And what you do is, you have to fit, the first step is what we call the input mapping. You really have to fit your new data set into this old data set that you have. And then you, now once you fit it, then you apply to the trained model and map this trained data set to what you are used to. But then imagine when you do the classification, your classification in this new old models may not be exactly what you're looking for, because the classification classes could be changing, or your objective could changing. So then you have to have another adaptation. This is called the TY, what we call output mapping, that really have to go through this to get the real output in the domain of your output domain. Okay, so this is a very clear and very simple graph. But if you put this together, then you realize that this is transfer learning. Okay, let me, before I go to the math, so this is, you think about this is the generic classification problems, but you can imagine removing this picture as this as ROP image, and then this is the DR image here. And then when you do the DR, you actually create a 400 times 400 times 3 of this cropped images. Then you already have the optimization problem with the feature extractor and the classifier. Then you have this model. What you do in the DR case is you fit this new infant image here, trying to fit it into your original model. Then you utilize the feature extractor to really get to the clear image. So the key to get classification is to find what is clear image, what is a healthy one is. And then you come down, you use the feature extraction. And then in this particular case, if you're looking for the ROP instead of a DR, you have a fine tuning of the classification and the features that you wanted to do, and then you get a new input. So in this case, the input is fitting the image, and the output TY is to actually adjust the output with the fine tuning in the classifier. Okay, so this is very, in this picture, this is exactly mapping this. And then mathematically, you basically can just say the definition of transfer learning is nothing but solving over the choices of the input or the mappings of the image fitting, and over all the mappings of all the output mapping, then try to solve this optimization problem. This is nothing, the way I wrote here, is nothing but taking the loss function and map this images, remap these images of the XT target task through this pre-trained model, and then compare. This is basically the output of TY. Then the output managed to output the XT with this the 3 triangle way, and then you compare this label data with this adjusted output, and then try to find optimization. This is nothing but rewriting this 3-way image. Okay, so now you look at this optimization problem. The first question is this well-defined optimization problem because of this class of TX and TY? And the good news is, yes, you can really characterize the transfer learning, saying that if I give you suitable choice of loss functions, and if the data sets are properly chosen, and which are usually, or if the data sets are not good, then you can, when you design the neural networks, then you can define the activation function to ensure that the boundaries are well defined. So then if you have this, then the procedure of transfer learning admits an optimal solution. Okay, at least you have the existence. And the examples of choices of loss functions include many of this, including the L2, including what people have done in KL divergence, and so on and so forth. And the data set just need to be compact, or as I said, if the data set are not compact, then you need to make sure the activation functions are properly chosen. And with this byproduct of this formulation and optimization existence, what we also can prove is one of the corollary is to say that when I look at the data images or classifications, I always have features, or I have always wanted to add more data to data analysis. And one of the corollaries is this, says that if you choose the proper choices of loss functions, and for example, if you choose the one we mentioned here, Bregman divergence functions, then you can successfully filter out irrelevant information or undesirable features without having negative impact on your model performance. So that's one of the corollaries that we can find out. So that's the first question that I try to understand, or we try to understand the mathematics of transfer learning in the optimization framework. Now, the second question is, now you have this optimization problem, you know their existence, and going back to the problem we had is when we try to do the ROP, we tried the DR image, or we can try the generic image. Now the question is, how do you measure the transferability? Okay, so when we measure the transferability, now we come up with this word, say transfer risk. Why is a transfer risk? Because you associate it with the 3 steps of the transfer learning. Each of the steps, there is a risk here. So when you think about the input mapping, fitting the data of the target task to the source task, you are basically comparing the distributions of the data in some way, okay? And so in this case, you already have this input transfer risk. And similarly, when you have this output of YS in the domain of YS, and you try to fit this into this, you also have a distributions of the data set in which you have to compare. So there's another comparison of this. So in the entire transfer learning, what you really are balancing is this transfer, is this 2 procedures of TX. The transfer learning is over the input mapping and output mapping, is a very, very subtle balance, a delicate balance between the TX choices and TY choices, and each of which are associated with some risk. And therefore, your entire transfer risk or transferability has to be dependent on the input transfer risk and the output transfer risk. So this is a balance. You have another divergence function or measurement to combine these 2, okay? So this is what I just said. So in the transfer risk, you have 3 levels. One is the input one, is comparing the distributions between the input data and the output data. And then you have also the transfer risk on the other end to compare the distribution of the output distributions. And then you have to have the balance to make sure that there's some desirable functions. And if you're interested, we can send you the paper. I'm not going to give you the detail, that you have to give desirable properties of these functions. Say it has to be non-decreasing. If you have less risk, then this function should naturally be less. And then if you have a direct learning, there's no transfer risk, it has to be 0. And then in the particular case, in people in domain adaptation, then it has to reduce to only the one side of this risk of the input risk. So you have to have a certain axiom for which this transfer risk functions have to satisfy, okay? But all in all, we try to put this axiom into this to the framework, going back to the analysis we had in the ROP and DR. So remember that when we do the transfer learning in ROP and DR, we show that the improvement of using DR or using the generic image, the improvement are in this. So according to the confidence of how much you're sure your classification is right, this is ROC, or how much sensitivity, how many you can clarify. So the DR dominate, as we show, dominate with the real image in terms of improvement from the direct training. Okay, these are the percentage of improvement. So DR, for example, sensitivity was close to 30%, where if you just use a generic image, this is the 27, it's not bad. And then these are classical medical metrics that we measure the performance of models. Now we have this new transfer learning mathematical framework, we try to put it in a divergence functions. So if I actually use, so the input is still KL and output also KL, for example, then I take just the linear combination of this. So this is CS, C, what is the notation I use? The CS, yeah, this L input and this out. If I take this as a linear combination of the KL with some appropriate parameters, then I can show that indeed, even in DR, there's a transfer risk improvement, the reduction of the risk, which is the improvement of the performance, is the same consistent with the medical criteria. So this is really a sanity test to show that the mathematical framework that we established here is consistent with the classical practice where people use the various medical things. Okay, so, and then similarly, we tried using the Wasserstand distance. Again, we take the linear combination of the input risk and output risk, and then with the generic, just we didn't really fine tune to the optimal lambda hyperparameter. And still you show that you can see using DR, using this is still better than using the image. And this is consistent if you just use the correct, using the medical things. Then we go to, the title is from medical to financial data. Then we actually try the financial data, okay, and see whether we can do something interesting. So we go with the classical portfolio optimization problem where you choose the D asset and look at their returns, and then you try to allocate according to this weight in each of the assets, okay? And then the criteria is to use the Sharpe ratio, which is when I make a, so I have a choices of R asset, and then when I try to make a linear combination of this asset, and then the way to choose the linear combination is to use the criteria of Sharpe ratio to get the maximal return versus the lowest possible variance. And then this is my source task. And I'm going to use the target task here to get closer to the source task, meaning that I'm going to choose the rate of different weights. And then I try to be close to the original task. And then I measure the distance of the returns in terms of Wasserstand distance, okay? So why I do this, so what are my source tasks? This is the framework of source task and the target task. What do I have in mind, really? What I have in mind is about transfer a portfolio from equity market from one place to another. For example, if I have a portfolio management in US, and I'm very successful in identify a group of assets, and then I try to see if I go to a country which I have very limited data, or I don't trust the data there for, say, certain part of countries, global places, well, then I try to transfer my asset allocation into corresponding industries with how relevant this practice would be. And so this is the framework. I'm going to, for example, from US to UK, what I'm going to do is I look at UK become my target task. And I'm trying to take the top 10 assets there and try to relocate. And then instead of doing the direct relocation, I take the US S&P 500. And then I try to see S&P 500, if I do also the top 10 performer, of course, 10 out of 500, you have many choices here, okay? And then I try to see the relevance of the performance. Here, I use the transfer risk to test maybe some sort of correlations of portfolio management or success between cross countries. And here's the picture that I found. So this is the US and UK. And I use the transfer risk again, use the Vasa time distance here, and then see the correlation between, this is not the best number we get, but probably ignore the number here. Instead of focus on this picture that I'm going to enlarge, you can see that this x-axis is the transfer risk, and this y-axis is the Sharpe ratio. You can see that from US to UK, this is about 1,000 data points. I try to see what are the correlations or distributions of transferability between US and UK. And what is interesting, I think, this is a very preliminary data I'm showing, I hope to show you a better one, is in fact, one of the surprising things for us to show is, you see, if you see the line of this above the red, what it shows is, in fact, the correlation or the transferability between US and Germany is on average better than US and UK. Okay, and the other transferability is this. So clearly, the portfolio, if you use the transfer risk, you believe it, the transferability in terms of portfolio management between US and Brazil is very poor. Okay, so you cannot really see that. But then US and Singapore transferability is very similar to US and the UK. So that's basically, without going to the fine tuning, we didn't really succeed yet in finish yet the fine tuning, but in just arbitrary linear combinations of this transfer risk we measured without fine tuning of the hyperparameter, it gets largely the impression that the transferability between US and EU is much better than transferability between US and UK and in general Singapore, and definitely better than the transferability between US and Brazil, and we had also other countries, but these are the different choices, representative choices. So these are the preliminary analysis we show how the transferability can be established using this transfer learning framework. So I think I'm running out of time. I have 50 minutes and I'm exactly here. So the summary of the work is, for the first time, we understood at least what exactly transfer learning in terms of an optimization framework. And then one can establish the feasibility whenever you start a transfer learning procedures. And you just have to make sure your choice function are correct, and also your data set is appropriately compact. And then this can build on this transferability, feasibility of transfer learning framework. One can go a step further to try to find out the relevance of different source tasks to the target task in terms of transfer risk. And we show that in the medical data analysis, the framework we used with a very simple framework transfer risk is very consistent with the metrics in the data in medical image analysis. And in finance, the transfer risk we're still exploring it's just the beginning. And we are hoping to see that there are certain ideas that one can do. But so far, what we found is one can find just very arbitrarily the transfer risk definition, and that is very much aligned with what we call the Sharpe ratio in the transferability. So I think I will stop here, and thank you very much for your attention.
Thank you, Xin.